My name is Zach Sample. For those of you that haven't met me before, we're actually doing a re-recording of this presentation as the first time the audio didn't come through. Greg has given me the fortune of being able to present a little bit about some of the things I work with on a day-to-day basis. So today we'll talk a little bit about simulation, specifically dynamic simulation, and how that relates to the virtual plant. So just a little background information about myself. I am a simulation project lead at Maya Technologies, and I'm currently working on my master's in chemical engineering from North Carolina State University. I've had 3 years of experience at Maya Technologies doing a variety of different simulations for different industries, ranging from the life sciences industry to petrochemical, specifically around ethylene, refining, oil sands, pulp and paper, and as of recently, a lot of mining as well. At Mine, I'm also one of the training academy lecturers, meaning that I give a presentation on how to use our Mimic Dynamics simulation software. I'm leading the Maya STEM initiative, where we go present at different high schools about controls, kind of as an intro controls 101 kind of course to generate awareness about controls. I'm a student liaison for the local AICHE section as well, and so I work a lot with the universities from that standpoint in the Missouri area. And as you're all probably well aware, I'm one of the newer additions to the ISA mentor program. So before we get any more or go any further, we should probably go ahead and define what is the virtual plant, right? So if I were just to read this and say a virtual plant consists of a dynamic process and I/O model integrated with an emulated control system in a virtualized environment. That might mean something to some people, but others that's kind of vague and nebulous. So we'll kind of go through it piece by piece. So first, it consists of a dynamic process and I/O model, meaning that it has realistic dynamic transitions of the process and I/O. Integrated with an emulated control system refers to the fact that this process model is being used and implemented against a copy of your offline production control system. And in a virtualized environment just refers to the fact that this is sitting on a server in the cloud, somewhere where it's easily accessible for use with operator training or for control system testing. And so we'll kind of get into some of those use cases as we go through this presentation. The virtual plant architecture. So I'm going to preface this with, obviously this is coming from one of our internal documents. I'm going to stick to just high-level description of what the architecture looks like. But so from a virtual plant architecture, I'm going to start on the right-hand side. That's the control side, and work our way backwards. So on the right-hand side, you'll see the operator or engineer interface to the control system, and interfacing with different control strategies, whether that's Delta V or whatever that may be, and then that has its control system I/O. There is then on the simulation side, we've essentially ripped this control system from the plant and have replaced the plant with a dynamic simulator. And with the virtual plant, we have real-time I/O communicating to the same control system I/O through an I/O bridge with different I/O models and then high-level process models on top of that allows you to essentially run your entire plant in a virtual environment. So, on the last part of that, I mentioned the idea of process models. So the process models can be very kind of an unknown of what level of process model is required, and a lot of times the word fidelity is thrown around as that kind of describes how accurate the simulation is. And so the model fidelity is really the simulation complexity or model rigorousness. And in describing it, it's also the similarity to real unit operations in steady state operation, in dynamic operation, or in transient. So all these pieces come into play. Now, I've organized this, you'll see in the image here, that I've organized into kind of discrete sections, whether it's tieback, low, medium, or high fidelity. But when we think about this, that's really not a good representation of it, because you don't say a simulation is low fidelity or an entire simulation is medium fidelity in most cases. Most cases it's going to be separated by maybe process area, or maybe you only care about this one key unit and the rest of it can be pretty low fidelity. So a lot of times this is more of a gradient than it is a discrete simulation fidelity. And the other piece of this is making sure that you match the model fidelity that you choose for your simulation matches to what your purpose for this simulation is. Part of that is a time investment, how much time you're going to invest versus the value you're going to get a return on it, and making sure you're not trying to invest too little time into getting a simulation where it doesn't achieve what you're trying to use it for. And so the objective of this presentation is kind of to walk through different levels of fidelities, what they mean, what they entail, and so we'll kind of start from the ground up. So the lowest of these fidelities is the tieback model that I talked about, and what this may include maybe your traditional first order filter plus dead time modeling. Now, this allows for very simple, very rapid modeling of your process model given the proper information. But there's some obvious detractions of doing this, and part of that's because A, it's a very simplistic view, and B, it requires a single linear dependency, which means that you can't really have interactions between variables, and it's always the same relation, essentially. So these things are limited in their ability to model your true process responses, and this becomes even more so, and we'll talk about this a little bit later, when you talk about more of these like integrating responses. And then the last piece is really this type of modeling, when you're dealing with tieback modeling, only models control variables. So if you have a control output, you're modeling the response to that controller output. So if we take a look at what this might look like from a modeling standpoint, what we have here is and those of you that are familiar with Delta B blocks may think that this looks familiar, but the one thing that you'll notice immediately is that we have outputs coming into the system and inputs going out. And that's because from a simulation standpoint, the inputs are going into the control system and the outputs are coming from the control system. But what we have here is we have some valve position that's coming back to us as the simulation from the control system. This valve position is essentially being scaled and filtered with a certain filter time, and then being sent out as the flow. So this is a very simplistic model, but it allows for the flow to change with a certain valve position as a controlled variable. Now, what this doesn't allow for is, you may notice there's no dead time anywhere. You can't define a dead time anywhere in here. And that is because A, this is often not known, and B, for purposes of speed and kind of a easy to control simulation, this is a very good way to get a base level without that dead time information. So this is truly the lowest level of modeling that would be there. If we wanted to add dead time, we'd probably add it after the loop tieback block before we send it back as a flow. Okay, so what we're looking at right here, and I'm going to pull this graphic up a couple times during the presentation. What we're looking at here is what are the capabilities of different modeling fidelities, and what we were just looking at is the tieback level of modeling fidelity, which really does only two things here. It provides static values for all the uncontrolled I/O, and it provides directionally correct process responses for loop I/O. So that's kind of all you're able to achieve with FOPDT models, and that's because they can only be attached to some control variable somewhere. So as we move forward, if we wanted to increase this fidelity, we're going to talk about that next. The other thing before we get to that is we're going to look at how these systems can be applied. So for example, in this case here, for tiebacks, is they're really only able to satisfy two different things. One, you can test the fundamental control system configuration, meaning is your I/O lined up properly? Are your control variables controlling the right variables? That can be tested. And the other piece is that it allows you to familiarize operators with the control system interface from a training perspective. So that's kind of the low-hanging fruit in terms of simulation, as it doesn't really allow you to train on any process interactions or process control through process control. So if we wanted to increase this fidelity by going to a low fidelity model, we might do things like starting to incorporate different dependencies. And an example of this might be incorporating the dependency of a flow on a pump state, so it doesn't just flow when maybe it's getting the controller output of some value that it gets flow. It may also require the pump to be turned on for that to happen. Same thing for maybe a handful of discrete valves, and we can start implementing those. We can also start incorporating dependencies on interdependencies of variables. So that may be on a heat exchanger. You may have both the temperature and flow impacting your heat exchanger flow. And for another piece that you may start adding would be incorporating simple basic calculations. So this may be things like starting to handle levels, if that's a controlled variable, not as a simple tieback, but it may also include having a integrated level where you're actually accumulating your flow rate over time and subtracting the outlet flow over time. And that'll allow you a true integrated response instead of a kind of a first order plus dead time model for your integrated level. Or this may be, similarly, you might be doing something with like the ideal gas law in order to simulate pressures in your system. The last piece here is you might also incorporate some calculations for some uncontrolled I/O. So up to this point, we've talked about only things where you have a controller variable that's directly trying to impact some value. You may not have a level control on a certain tank, and you may start using your flow controls to then simulate what your integrated level response is. So what this might look like, we're going to look at a couple of these examples, is from a flow path validation standpoint, and this is adding something that's going to be a requirement for flow to happen. If we start on the left-hand side, we'll notice this is very similar in that we have a valve position coming back to us, and then this is being fed into a tieback block that's going to scale it up, and then this is going to go out to a flow. But what we've added to this model is we've also added a path condition. So this may be that there's a valve that must be open, or maybe that there is a pump that must be on. And then we've also added constraints so that it doesn't go outside of a certain range, right? So we have an input and kind of an input for the minimum and maximum of what can be achieved. So the next example that I have here would be what I was talking about for creating an integrated response. We may add up all of our flows into an integrator and accumulate those so we can get a true integrated response. From this, we can also simulate, maybe attach that to one of our discrete values that may be presented back to the control system as well. So in this case, we're also providing a level switch as a discrete value back, which would otherwise not be presented as part of the simulation traditionally, in that it's not a control system response to a controlled variable. So we're going to real quick go over an example that we had of a low fidelity implementation. This was a recent project I worked on where they wanted to integrate a simulation system with 31 physical controllers and 7,000 I/O, greater than 7,000 I/O. And the reason they want to do this is because this was a life sciences company that required a validated system. So for those of you that are in the industry, you can certainly appreciate that. But what they needed was some way to test their control systems, specifically their batches, in an offline environment and port that over to the production system. And they have to do this frequently because they're a multi-product facility. So they're continuously making adjustments to product and then porting those over to the live production system. So it's very important that the test platform is essentially directly portable without modification between the production controls and this offline virtual plant. Now, what we did as a first pass, and we'll circle back around on this as we're actually in phase 2 on it. As a first pass, we did only tiebacks. Now, this allows them to do a checkout and validation of their control system before it's forwarded back to the production system, and allows for some simple checking of your control system for directional responses. But what this doesn't do is it doesn't really have enough in there to test all your sequences. So anything that may be relying on discrete valves, anything that may be relying on integrated values, those things may not be incorporated yet. So we'll actually talk about what we're doing in phase 2 as we go, where we're going to add more modeling on top of the existing timeline. So what we kind of covered here is we covered a low fidelity solution, and what this also includes in addition to the low fidelity model, and this may also include having directionally correct process response for dynamic I/O. And what that means is that's different from the loop I/O, in that it's I/O that may be associated with controls, but is not it's indirectly responding to control system level. And then having simple I/O interactions where you may have a PV/nRT calculations where the temperature of the tank that you may be controlling will directly correspond to maybe the pressure in that tank. So those kinds of things. Now, what this can then be applied for at this low fidelity level is this can be applied also for familiarizing operators with control strategies, as you can start building in their understanding of some of these process interactions and how the controls function, and also allows for rigid training at the program process response. Now, what do I mean when I say rigid training? That seems a little ambiguous. Is really at this point your process is limited to still kind of tiebacks and basic calculations. You're not going to get in any of these unforeseen situations or scenarios that may require training. So you're limited in training scenarios where you are essentially programming how the process is going to respond specifically for that training scenario. So that's kind of the limitation of the low fidelity model. So if we wanted to increase our fidelity beyond this low fidelity, we do so by starting to incorporate a pressure flow method. And this will automatically include all of those dependencies that we were talking about. Okay, is the pump on? Is the valve in place? Those kinds of pieces, right? And then incorporating a material and energy balance, meaning that we're integrating levels between the tanks. We have a thermal mass in our system. All those pieces come into play, and those start coming into play through our first principles engineering calculations. And that may include having pump curves or simple heat transfer calculations. All these things start being implemented in the system to kind of have a cohesive simulation. So to kind of give you an example of what this might look like, and I've graded out a piece that we'll talk about a little bit later, but essentially what we have here is what I would call a more advanced model. So you may notice these blocks look distinctly different. They have gold lines in between them, and that's because these blocks are simulating process equipment instead of just a single function or a single calculation. So like this vessel has an integrated level with a calculated thermal mass and temperature, with a vapor pressure, et cetera, and then these thick lines, the reason they're thicker is because they contain more information. On each one of these streams, as we call them, they include everything from mass flow to temperature, pressure, viscosity, composition. All of this information has been passed block to block like it is in the true process. So this is how you can start seeing we can have flow from one vessel and take into account all the valves and all their open percents and that impact in a pressure flow network to get flow in between the different vessels. Now, we actually I'll actually have two examples here, and the first of which is an example that I've had recently on a mining project. We built the system in parallel to their W control system development. It was a greenfield facility, and the idea of this project was in order to not only allow them to test simple control strategies and sequences for FAT purposes, but also train their operators on how to run the control system. This higher fidelity model, than what was included. So obviously, most control system integrators will include some level of modeling. Our model identified over 50 issues in the previously FAT database prior to commissioning. Now, while most of these things were minor interlock, alarm, graphic fixes, those kinds of things that we were able to identify, some of these things were much more critical. And there's the things that you didn't see. So like, for example, there's initial simulation they were using for the FAT had all of the flows set to constant non-alarming values. Now, that's not really a realistic situation, and for example, they had alarms that would go off if you had zero flow. So essentially, if everything was turned off, your entire plant was alarmed, which there wasn't a real reason for that, and actually normal running condition was to have the pumps off because it was a batch operation. Other major issues that were that we identified included a hydrogen peroxide addition miscalculation where the mole ratio was off, so that would otherwise have kind of serious implications on how much hydrogen peroxide they were adding, potentially causing a runaway reaction in one of their tanks. They had a sequence that could never reach its exit condition. This was kind of a situation where they didn't actually control the level, they controlled the flow in and the flow out. The sequence asked for both flows to be the same, so once it actually achieved this state where it was trying to achieve the equal flow in and out, of course the level would no longer change at that point. But the exit condition for the sequence was that the vessel ran dry. So obviously that's not going to happen. So we ran into things like that. And then the most important one that we were able to identify was a contradiction between design documents and the control configuration, where we identified that one of their tanks that required a safety permit for a specific quantity was actually larger than the permit that they kind of had already acquired for a site. So they had to go out and request a larger safety permit that would have otherwise been an issue. And this was kind of just a function of running into contradictory design information when creating the simulation. For my other example, I talked about that not from life sciences for our low fidelity simulation, but we've since been starting a phase 2 where we're actually doing this medium fidelity modeling. And what this does is it adds physical meaning to your models, and that's because you're using equipment like we saw in my example. And the reason they want to do this is because it makes maintenance much easier. So if they were to de-pipe a valve, you don't have to go dig through your code and say, okay, I need to remove my conditional statements from here and here and tweak my calculation here. You literally just tweak your process model to route through a different valve or bypass a valve. You can, and so it's much easier to do that, and then it's easier to scale at that point as well. So you can do pieces of it at a time. and go to a much higher fidelity as necessary. So maybe if you wanted to do a bioreactor, you can add this to your infrastructure that is in place. So we're currently underway on that, and that will allow them not only that, but it also allows them to test full batch functionality, because you should be able to achieve all of them. So there's a heating sequence or a fill sequence or an empty sequence. All of those you'll be able to run through a batch sequence. So looking back, taking a look back at this table, you'll notice that our medium fidelity, again, this is coming from our internal documentation. Ignore the dynamic core, as that's kind of our own verbiage. But the process model fidelity, that's the medium fidelity. You'll notice that there's a big jump at this point, where we added a lot of functionality to the process model, and that's because once you start adding physical meaning to the model, we essentially added the material and energy balance, the pressure flow network, as I said before. Your equipment is modeled per your plant design specification, means it's easier to maintain as if maybe equipment changes, maybe you change your valve, maybe you change your pump situation. All of those things can be implemented into your simulation very easily because it's based off design. And then having a first principles-based process interactions that is a more useful simulation. So what does this look like in terms of use? What this adds to the functionality of the simulation is it adds to the ability to test your control strategies. So this gets back to exactly what that life sciences project where they wanted to test their batch strategies. They can test those in full, but also it allows you to test on simple process upsets and operating procedures. Where if you were to, let's say, overheat a vessel, or maybe you were to empty a vessel that shouldn't be emptied, all those things you can kind of simulate for training purposes, and you get directionally correct responses for all of those. Now, the highest level fidelity, this one we're going to talk about, is when we start implementing these more advanced engineering calculations. They may be vapor-liquid equilibrium calculations, or implementing reaction kinetics, or improving model transitions to include your valve characteristics or process non-idealities. And we'll take a look at what that may look at like. You'll notice that this isn't grayed out anymore. Our distillation column here on the bottom left. In this case, we have a full tray-by-tray model of their distillation column, and then that is being used as part of their processing. Otherwise, in principle, it is the same idea, and this is why I say that this is more of a gradient scale. Everything else is the same as what it was for a more medium fidelity solution. So I mentioned that one of the things you might start improving is getting the correct valve characteristics, and this may be anything from implementing the correct valve opening for a certain control system output, as this has a big change in where your plant is going to operate at. If that's something that your operators know that it runs at 50%. If it's going to run at 50%, you'll need the right valve characteristic in order to get that to have the correct response. The other pieces that you may start taking into consideration, you may start taking into consideration the design, see the leakage of a certain valve, or more importantly, some of these other pieces that are often overlooked is going to be your valve hysteresis, your deadband resolution, your velocity gain. And these have very big implications on how your control system is able to control your plant. So just as an example of one of these higher fidelity simulations, we did one for a refinery, and we did specifically around their fluidized catalytic cracker, where we did full component tracking of their heavy oil, and it was a very complex process that they needed training on, as it was kind of the unknown to their operators. And the big difficulty in this is one, handling your plug flow reactor, and two is handling the circulation, as a lot of the values are kind of inferred. So some of the high fidelity modeling that went into this was, of course, getting those reactors to react appropriately. And then also, for example, we were talking about valve characteristics. We added to these valves in between our reactor vessel and our regenerator. These are actually gate valves, and because there's a fluidized catalyst flowing between them, you get essentially little to no flow between them for the first 30% or so that they're open. So we simulated that valve characteristic so operators would get the right process response, as they actually control this thing almost completely based off pressure differentials across their valves. The other thing that was a very, very big change that I actually didn't find out until later in the project was the other big driving factor on this was the ability to start up and shut down this particular process area. And it's because when you shut it down, you basically pull feed from it. This is a reaction that is kind of that is required to continue in order for the carbon to continue to be a liquid, right? And because it is, or I suppose, yeah, in order for the carbon to continue to be a liquid as the carbon coat builds up. Now, as soon as this becomes no longer fluidized and drops below a certain temperature, this reactor vessel essentially freezes up and this carbon just starts layering on. And actually what happens is if they do it wrong, if they shut down the plant wrong, they have to take apart this vessel and drill out the inside of the vessel as it just filled up with carbon. So what they actually do is they fill it up with this heavy oil, and this heavy oil is then essentially burned, and this allows this system to stay hot enough that this buildup doesn't occur. Now, the other thing they do is that the way they pressurize the system at that point is they add steam instead of the feed. Now, what this then requires is that essentially you have an entirely new steady state operation where you have steam, and you'll notice in this picture here that this goes over to a fractionator, and this column then collapses because it loses pressure. Everything feeding the column is just water. So this obviously is much more complex of a situation to model. But we were able to achieve both of those different steady states and allow operators to then start up and shut down the plant, which is a very difficult thing for them because it's something that they really only did 2 or 3 times a year. So by the time an operator got experience with it, you were kind of worried about, okay, do they remember what they're doing? How many times have they done this before? So this gave them more time in front of it so they knew what to expect from starting up and shutting down the system. Another example, and this kind of speaks to the applicability of these high fidelity simulations, is an example from one of my most recent projects in mining, and this was a high fidelity front end crushing simulator for an iron ore mineral processing facility where they did full component and particle size tracking throughout their plant. And they needed this plant because and this is probably the this customer specifically used their simulator for more than I've seen any other customer use this for. They kind of took advantage of all aspects of it. They wanted to use it for operator training and specifically to train operators on their profitability, where they're scored against, okay, how much product did you make, what was your throughput, and what was your efficiency, so how much product were you losing while you're getting this throughput. They wanted to use this to improve their advanced process controls, specifically to kind of play around with the idea of auto starting stopping different equipment, or auto switching equipment if there was a certain case that needed it to do so. And some of this was also in both cases accounting for the power draw. These large pieces of equipment have a massive power draw, and taking this into account into your profitability and what your advanced process control is doing. The other pieces is also included is they want to train their management team on how to make proper decisions on when should you be pushing for efficiency or when should you be pushing for throughput on your from an operations management perspective. And then the last piece there is this is also a test bed to improve their kind of their HMI, and that's because they right now their graphics are very colorful, and as many of you have already aware, there's kind of a push to get away from that. It's very difficult to operate when there's a bunch of flashing lights at you all the time, or a lot of color on the screen. And they'd like to go grayscale, and there's a lot of pushback from the plant in order to do so, but this allows kind of a test bed to show this is what it would look like, doesn't this look cleaner? So that's kind of the multifunctional use of a virtual plant. This will be kind of our last look at this chart, but on the far right side we have a high fidelity option here, where we start adding into the things I was talking about, from reaction kinetics to vapor liquid equilibrium, or component and phase size tracking, and even handling some of the transitions of the process, maybe through full startup and shutdown. And what these additions allow you to do is start getting into these more advanced uses of the simulation. It includes maybe tuning some of your loops, or doing some control parameter studies. And then doing training on some of these process interactions, or complex process interactions, or upsets in operating conditions. Some of those things like I was talking about for starting testing on startup and shutdown. So that's kind of the end of my presentation, and hopefully that gives you an idea of a little bit about some background about how to choose the right fidelity for your simulation. What we're going to do here, since this is actually is actually a re-recording of the presentation, I'm going to read through the questions that were asked and kind of answer them just for those watching that weren't able to participate live. So give me 1 second to get those pulled up. Okay, so the first question that I got here was from Greg, asking what fidelity do we see customers using most commonly. And my answer to that is that realistically it depends on the use case, but the most common use is honestly probably the low fidelity simulation, because once you have the I/O in place, it's easiest to start adding some simple relations in your process to start connecting I/O, or doing some low fidelity modeling. But from a training perspective, the most common that we see is probably in that medium fidelity, where you can get more dynamic process responses and more physical meaning to what your process responses are doing. And I think actually the direction that this is headed is that control system simulation is going in the direction of needing medium fidelity models as we, for purposes of FAT, kind of like what I discussed in my example. And the reason for that being is that as these processes become more and more complex, or control strategies become more and more complex, that requires the process model underneath of these controls to be more robust. And so that's kind of the direction that you see that going. Marcia Wisely then went on to ask and saying that one of the challenges that she saw in using models in her job was trying to find the different levels of fidelity, and kind of defining the boundaries between portions of the model that need to be this medium fidelity as for control system development. And I guess my response to that was that that's always a difficult task, because there always tends to be a little bit of scope creep on that. And what we've actually found is it's almost easier to go by process area instead of individual pieces of equipment, because by the time you do individual pieces of equipment, you start running into difficulties of, okay, is that pump required, or is this pump required? And once you do it by process area, it's much easier to define, kind of roping it off as a whole thing altogether. That way there's a lot less questions. So that's kind of what we found. So the next question was Marsha wisely asked what kind of modeling we were doing for the pulp and paper and life sciences. For pulp and paper specifically, we've been doing a lot in terms of digesters. I've been working specifically with the K-Mir digester that we have as kind of one of our newer models. But we've also worked on several projects of different batch digester systems that are out there. From the life sciences standpoint, a lot of what we've done, because life sciences, a lot of it is just pumping liquids around, it's heating pieces of equipment and having different batch operations in place. A lot of that has been the medium fidelity solution that we talked about, where we're able to move things around, but we're not doing that full component tracking. We're not doing the full vapor liquid equilibrium, those kind of things, because they're not as required as much for life sciences, and that still allows for them to test on their control system. The exception, we've had a couple of exceptions to that, obviously, and we've done some bioreactors as well. The last question that we had was that Alice and Asiri asked if we have difficulty finding the time to do more than the spotty low fidelity and tieback modeling for operator training. We normally don't have operating problems, but when we do, the operators may have gotten what they need to do. How can a medium fidelity simulation help us here, and how can we make the time involvement minimal? And my answer to that is really the medium fidelity simulation is, again, I think you're best off starting with separating things off by process area. And that kind of allows you to minimize the time involvement by not trying to handle your whole process at once. But the intent of medium fidelity is that it's not a large time involvement. If you have the basic set kind of simulation or engineering design information, you can very rapidly put this type of model together, because it's just moving material around and heating and cooling. So it's not overly complex. So it's designed to be very quick. But from the standpoint of having low fidelity, there's obviously that big gap that we discussed between the two. Okay. I think that was the end of our questions from the live presentation. Greg, did you have anything else?
No, thank you, Zach. That was very good, and we'll go from here. Thank you.
All right, perfect. Thanks, Greg.